So let's begin. Acid-base titration are usually defined the amount of amino acid or basic substance through the acid-base reaction. This method is essential for various applications ranging from industrial process to research and environmental monitoring. To understanding the principle and step of acid-base titration provide a foundation for many scientific and practical endeavor. Imagine you have a mystery solution and you want to know how acidic or basic it is. To figure this out, you can use another solution with a known concentration called the titration. By carefully adding the titration to the mystery solution, the analyte, you can measure how much the titration is needed to neutralize it.
Titration involves apparatuses such as burette used to measure volume of added solution currently, conical flask used to hold and measure analyte, retort stand used to attach clamp to hold burette during running titration, and bulk pipette used to put an accurate volume of the reactant in the conical flask.
In acid-base titration, there can be two different methods used. The first method, which is a direct method, uses a titration of two different solutions. The first solution has a known volume and a known concentration. This is usually the titrant. The second one has a known volume but an unknown concentration. The volume that is used in this titration or determined in this titration will be used to determine the unknown concentration. Now, back titration or indirect titration uses a two-stage analytical method or two different reactions. The first reaction is between the substance of interest, or let's say reactant A, with a reactant B which has a known amount of concentration in excess. The second reaction involves a normal titration to determine the amount of unreacted reactant B that was in excess. It should be noted that back titration is used when one of the reactants is volatile. For example, it uses ammonia, or an acid or base that is an insoluble salt, for example, calcium carbonate. Or usually when the particular reaction is too slow, when we use weak acid and weak base.
Ways to clean the apparatus. Before use, first, initial rinse. Use distilled water to remove visible residues. Second, detergent wash. Clean with detergent solution and a brush. Avoid abrasive material. Third, rinse with tap water. Truly rinse to remove detergent. And fourth, rinse with distilled water. Multiple rinse to remove detergent. After use, empty residual solution. Pour out any remaining solution from the apparatus. Second, rinse the tap water. Rinse thoroughly to remove residual chemical. Third, detergent wash. Use a mixed detergent solution to clean the apparatus. Scrub with appropriate brush as needed. Fourth, rinse with tap water. Rinse again to remove detergent. Fifth, rinse with distilled water. Perform several rinses to ensure complete removal of impurities.
Now, let's look at example of result. Let's say you have a 25 mm sample of hydrochloric acid of unknown concentration and you titrate it with 0.1 mole sodium hydroxide. You find that it takes 30 ml of the sodium hydroxide to reach the equivalence point where the amount of acid equals the amount of base. And for the explanation, during the titration, you added 30 ml of 0.1 mole sodium hydroxide to neutralize the hydrochloric acid in the solution. By calculating the moles of sodium hydroxide added and using the 1:1 stoichiometric ratio between hydrochloric acid and sodium hydroxide, you determine the moles of hydrochloric acid present in the original sample. And finally, by dividing the moles of hydrochloric acid by the volume of the hydrochloric acid solution, you found the concentration of the hydrochloric acid to be 0.120 mole. And for the diagram explanation, the titration curve is the blue line and it represents the change in pH as sodium hydroxide is added to the hydrochloric acid solution. The equivalence point is marked by the red dashed line at 30 ml of sodium hydroxide added. At this point, the amount of sodium hydroxide added is exactly enough to neutralize the hydrochloric acid in the solution. And lastly, for neutral pH, the green dashed line at pH 7 indicates the neutral pH at the equivalence point, typical for a strong acid, strong base titration.
So, in conclusion, acid-base titration is a fundamental technique that, by progressively adding a known titrant until the reaction reaches its equivalency point, allow for the exact measurement of the concentration of an unknown acidic or basic solution for the purpose of assessing and managing chemical reaction, guarantee product quality, and upholding environmental regulation. This approach is crucial in a number of scientific or industrial domains, including chemistry, biology, medicine, and environmental science. The titrant, analyte, and indicator are essential components of this simple procedure, and its accuracy and dependability make a vital instrument in analytical chemistry.